Okay, so today we're talking about colligative properties. And here in Minnesota, we're familiar with colligative properties. You just may not have heard them called that before. So the essential question today is how are boiling point and freezing point affected by colligative properties? And you'll be able to answer that question if you can define colligative properties, if you can explain what happens to particle behavior during boiling and freezing, and if you can explain why adding a solute to a solution changes the boiling point and freezing point. All right, so definition of colligative properties. They are properties of solutions that depend on the number of particles in a volume of solvent, in other words, the concentration, and not on the mass or identity of the particles. And these colligative properties affect the physical properties of the solvent. So there are three types of colligative properties. Boiling point elevation, because boiling point is a physical property of, let's say, the solvent water. Freezing point depression or freezing point lowering. Again, freezing point is a physical property of a solvent like water. And then vapor pressure lowering. And we haven't really talked about vapor pressure, so we're going to focus on boiling point elevation and freezing point depression. All right, so one of the things that kind of brings this definition home for students is when I tell them that we experience colligative properties on a regular basis in Minnesota because we tend to throw chemicals on our sidewalks to make them safer to walk on. And what I like to point out right away is that you could use sugar on your sidewalks as an ice melt just as easily as you could use salt. And most people look at me like I'm kind of crazy when I say you can use sugar as an ice melt, but it doesn't matter what kind of particles you throw on the ice to get the freezing point to go lower. What matters is the number of particles you can get to dissolve in the water that's at the surface of the ice. All right. So the identity and mass of the particles does not matter. What matters is how many particles you can get to dissolve. All right, before we can talk about boiling point elevation or freezing point depression, we first have to know the mechanisms that occur for boiling and freezing. So let's start with boiling. And again, just taking you back to this model of the water molecule that we looked at earlier this week. When water molecules get close to one another, they're attracted to each other. And hydrogen bonds form, because it's called a hydrogen bond, because the hydrogen, which is positive, has a positive charge, is attracted to the negative end of the water molecule where the oxygen is. And again, they're overall neutral, but because the electrons are pooling on the oxygen end, the end tends to be negative, while the other end, because there are no electrons pooling at that end, tend to be positive. So they easily are attracted to one another to make these hydrogen bonds. And that means that water is typically a liquid at room temperature. So it's the hydrogen bonds that hold the water molecules close enough together to keep them in that liquid phase. When we heat water, which is what we have to do to get it to boil, either that or change its pressure drastically, but under most circumstances, heating is the easiest way to get water to boil. What we're doing is we're adding energy. and the energy we're adding is kinetic energy, or the energy of motion. And so the water molecules start to move faster. And as they move faster, that extra movement or vibration causes those hydrogen bonds, even though they're pretty strong, it causes them to break. And once they break, then the water molecules are free to move even faster. And really fast moving water molecules are vapor molecules or gas molecules. And so if we get it to move fast enough, we can see that the water molecule moves into the gas phase. It doesn't disappear, it just moves fast enough to go into the gas phase. All right, so if we're adding kinetic energy by heating water, at what point do we say this is the boiling point? And sometimes you can see little tiny bubbles forming on the surface of the pan when you're trying to boil water. But we usually don't say that the boiling point is till you see the big rolling bubbles. So what's happening when we reach that boiling point? So as these molecules within the water start to move faster, so I'm just magnifying this light blue dot in the middle of the water molecules. These water molecules are liquid, and they're attached to one another with hydrogen bonds. But some of the molecules, like this one, will get to moving fast enough that it will start pushing the water molecules around it out of the way. So because it's darting around really fast, it's colliding with the water molecules around it, and it exerts pressure. Pressure is just push, and whenever there's a collision, there's a push. So the water molecules that are able to escape the hydrogen bonds and form gas molecules start pushing on the water molecules around them. And that's the beginnings of a bubble. So the little circle that I've drawn here around it is the beginnings of a bubble. It's easy for us to think of bubbles as actually as being empty space, but what we have to keep in mind as we go through this process, those bubbles actually have water molecules in them. It's just that they're in the gas phase. They're moving really fast, creating pressure on the water molecules around them, or pushing them out of the way. And they're moving a lot faster than the liquid molecules. All right, so at the same time as we're increasing the kinetic energy, and these gas molecules are starting to break away from the hydrogen bonds and go into the gas phase. At the same time, we have air molecules like oxygen, carbon dioxide, nitrogen, argon, all of those particles above the surface of the liquid are being pulled toward the earth by gravity. And as they get pulled toward the surface, they create pressure as well. They start colliding with the surface of the solvent. And as they do, they create pressure as well. And so right at first, the few gas particles that are able to escape or water molecules that are able to escape into the gas phase end up not forming bubbles because the air pressure pushing down on the surface causes them to collapse. So if the air pressure of the air at the surface is greater than the pressure being created inside the bubble, then the bubble's going to collapse. All right, so once enough water molecules have escaped into that gas phase, so now we've got several gas molecules pushing the liquid away and the bubble forms. When the pressure of these gas molecules in the liquid equals the pressure pushing down, at that point we have what's called equilibrium. And so the air pushing down can no longer collapse the bubble. So the bubbles stay intact. All right, that's the boiling point. So let's take a look at a more formal definition here. This is another diagram of the water molecules. So we're just looking at the very edge of this bubble, magnified. So we've got liquid over here, gas bubbles at the surface of the bubble are constantly moving into the gas phase. Some of them slow down again and move back into the liquid phase. So it's kind of a back and forth here. But once we reach the equilibrium, where the pressure that these gas bubbles are creating is equal to the atmospheric pressure pushing down, that's when boiling occurs. Okay, so this is a definition that you're going to need. All right, so here I've blown up the edge of the bubble from a couple of slides ago, and here I'm showing the hydrogen bonds that are connecting these liquid molecules to one another. And as they start moving faster and faster, it's important for us to recognize which of those particles are most likely to enter that bubble or the gas phase when we talk about colligative properties. And so what I'd like you to notice here is that the particles that are at the surface of the bubble, or even at the surface of the pan of water that you're boiling, are only connected to the molecules to the sides and beneath them. So if we look at this water molecule right here, we can see 1, 2, 3 hydrogen bonds. Whereas this molecule, which is really inside the liquid, is attracted to 1, 2, 3, 4, 5 different molecules, possibly even 6. And so in order for this molecule on the inside of the water to break into that gas phase, it has to break more hydrogen bonds. So the ones here at the surface of the bubble or at the surface of the liquid, which have fewer hydrogen bonds because there's none on this side of them, they're the ones that are most likely to break enough hydrogen bonds to go into the gas phase or to go into that bubble. All right, why does that matter? The colligative properties is why it matters. So what happens to the boiling point when a solute is added? Okay, so let's say these red crystals or red dots are sugar crystals or sugar molecules. So we've added some sugar to this water. And here's that water molecule that was poised to enter the gas phase a little more easily than the others. But now with this sugar molecule right here, the sugar molecule or the solute gets in the way. So now it takes more energy for the water to boil, because not only does it have to break these hydrogen bonds, but it also has to get past the solute particles to get into the gas phase. And a lot of times it slows down just enough that it gets drawn back into the liquid instead of going into the gas. All right, so what happens is, because it takes more energy for the water to boil, the water has to get hotter. We have to add more kinetic energy to reach that boiling point. So if this is water, instead of boiling at 100 degrees Celsius, maybe now the temperature has to get up to 110 degrees in order to boil. And that's important because once a substance reaches its boiling point, it stays at that temperature until all of the water boils away. And so if you're cooking pasta, if the boiling point of pure water is 100 degrees, that's the temperature that your pasta will cook at. But if you can raise the boiling point to 110 degrees, that's the temperature it will cook at, and it might cook, it will cook faster. All right, so boiling point elevation again is the boiling point. We say that the boiling point of a solution's a mixture, is always higher than the boiling point of the pure solvent. And again, we don't have to specify what that solute is. Just the presence of any solute will cause the boiling point of the solution to be higher. So again, adding that solute interferes with the molecules trying to escape the attractive forces of the liquid. And the attractive forces are those hydrogen bonds. All right, so now let's take a look at freezing. So water molecules slow down or lose kinetic energy when heat is removed. You've probably heard this before, but there's no such thing as cold. There's only the absence of heat. So when you cool something off, it's because you're removing heat from it. And again, that heat is in the form of kinetic energy or the energy of motion. And so if we're removing kinetic energy, the particles slow down. And when they're slower moving, it makes them easier to bond together using those hydrogen bonds. So if you can kind of picture in your head for a second, a bunch of little kids out on the playground, and they're playing a game where they have to grab somebody's hand and hang on. Only they're running really fast as they do that. So as they're running really fast, it's difficult to grab onto another child's hand and hang on because the motion is going to make them let go or make their aim really bad to begin with. And so if they slow down, it's much easier for them to grab each other's hands and hang on. That's what's happening with the freezing point. So as the particles slow down, it's easier for the attraction to create those hydrogen bonds. And as they create those hydrogen bonds, the particles get more organized. And you can see that this is water, for example. And water, because of those hydrogen to oxygen bonds, tends to form a hexagon shape, which is why ice crystals or snowflakes are hexagons. All right, so we've got slower moving molecules. It's easy for them to get drawn into the crystal shape by the hydrogen bonds because they're moving very slowly. So the freezing point is the point at which the attractive forces between the particles of a pure solvent is great enough, so the attraction is great enough to overcome the kinetic energy or the energy of motion of the particles in the liquid phase. So if we imagine this molecule right here still being in the liquid phase, it's still moving quite a bit faster than these particles are. So once it slows down enough, it will bond to the rest of the crystal and go from the liquid phase into the solid phase. All right, so then what happens to the freezing point if a solute is added? It's similar to what happens when the solute is added to the solvent for the boiling point. The particles literally get in the way. And again, it doesn't really matter what kind of particle it is. What matters is how many particles are in the way. So that when those water molecules are starting to try to form these hydrogen bonds, they are still moving fast enough that this particle getting in the way prevents it from forming the hydrogen bonds that will allow it to organize into the crystal. So the particles get in the way. Okay, here's another way to look at it. Focusing on this one on the left here for just a second. We're taking just a a small part of the surface and we're blowing it up. And this is the surface of the ice. The ice crystals down below, notice that they can get much colder than 0 degrees Celsius. But when this freezing process is occurring, the energy that would have been used for motion is used up to reform the hydrogen bonds. And so just like boiling, the temperature levels off during the boiling process, the temperature levels off during the freezing process. So it prevents the ambient temperature, or the temperature of the air above it, from allowing the temperature at the surface to go any lower than 0 degrees Celsius. Because even though those particles might be slowing down, the energy that was used for the motion of the liquid is being used to create the hydrogen bonds. Okay. Once we add a solute, notice how the freezing point has changed. So when there's no solute, freezing of water, for example, occurs at 0 degrees Celsius. But if a solute is present, it interferes with that bonding process, so freezing can't occur at 0 degrees. And so since the air temperature and the temperature of the ice below it is colder, it will allow that water at the surface to get down to -5 degrees Celsius, or maybe -10 degrees Celsius, or maybe -30 degrees Celsius, depending on what how much solute you have and whether this is water or a different solvent. So the colder air temperature allows the temperature at the surface to drop below 0 degrees Celsius, because the solute particles are preventing it from freezing at 0 degrees Celsius. So then once the temperature has dropped enough for the freezing to begin again, the temperature will remain at that lower freezing point until all the particles have become part of the crystal. So when we're making ice cream, homemade ice cream, we always add salt to the ice. And the reason for that is because the ice cream mixture that we're trying to freeze has a bunch of solutes in it. So we start with primarily water in the milk, and then the milk has protein and fat solids, and we also have probably a little bit of salt and some sugar particles that will dissolve, as well as maybe some vanilla molecules. And so those all lower the freezing point of the milk solution that we're trying to make into ice cream. So if we add salt to the ice that we're using to freeze the ice cream, it lowers the freezing point of the ice as well. And so the temperature is allowed to drop below the 0 freezing point, and it gets colder and freezes the ice cream mixture. So the freezing point of a solution is always lower than the pure solvent. That's why we call it freezing point depression. And again, it's just because the solute interferes with the attractive forces of the particles. So it's harder for them to organize into the crystal because of the presence of the solute particles. All right, so the stuff that we throw on our sidewalks in the wintertime in Minnesota is often called ice melt, but it's not really melting the ice. The surface of the ice on the sidewalk is constantly melting and refreezing. So there's always a thin layer of water on the surface. And that's why it's so slippery. That thin layer of water that can easily move reduces the amount of friction, and it gets very slippery. So when we throw the salt on the sidewalk, it doesn't cause the ice to melt, but rather the water molecules at the surface that have absorbed enough thermal energy from the sun to melt can't refreeze because we've lowered the freezing point. So there's constant melting and refreezing at the surface. By throwing the salt onto the sidewalk, it lowers the freezing point, and so the water that's already melted can't refreeze. Okay? All right, so at the beginning I said you could throw sugar on your sidewalk and use that to make your sidewalks safer to walk on. So why don't we use sugar? Well, for one thing, it would be a sticky mess. And for another thing, we're trying to get as many particles to dissolve in the water as possible. And sugar is a covalent compound. And so when sugar dissolves, the water molecules surround the sugar just like they would any other compound because it has a slightly positive and slightly negative end. But the sugar molecule itself, that's made up of carbon, hydrogen, and oxygen, doesn't break down. So one molecule of sugar will dissolve to become one solute particle. Ionic solids, though, when they dissolve, break apart into their ions. So if we look at a unit of sodium chloride, one formula unit of sodium chloride, if it dissolves in water, it's going to break apart into a sodium ion and a chloride ion. So we get two particles for each unit of sodium chloride that dissolves. Now, if we go down here to calcium chloride, which is made up of a calcium and two chloride ions, once it dissolves, we have three solute particles. And so the salt that they throw on our streets is usually not sodium chloride. It's usually something like calcium chloride because they can get more particles to dissolve or when they dissolve it than if they were to dissolve either the sugar or something like sodium chloride. So the more particles you can get the substance to dissolve into, the more interference you have and the greater the boiling point elevation and the lower the freezing point depression. All right, just a couple more examples of how colligative properties are used. And again, this is one that we're familiar with here in Minnesota with our temperature extremes. In the wintertime, our temperatures can get into the degrees below zero that are on this label, negative 34 degrees Fahrenheit. And the air temperature isn't going to get above the boiling point, but the temperature in our radiator certainly could as it cools out the engine. And so antifreeze is a liquid alcohol that's dissolved in water. And depending on how much of it we put in the radiator, it can affect the freezing point by taking it down to negative 34 degrees Fahrenheit, or it will protect the engine or the radiator from boiling over up to 265 degrees Fahrenheit. Okay. Now, if we add more particles, so here it's saying you can add 70% of the antifreeze to 30% water in your radiator. Notice how it increases the protection because the freezing point goes all the way down to negative 84 degrees Fahrenheit, and the boiling point of the water in your radiator goes all the way up to 276 degrees Fahrenheit. Okay, we often add salt to our water, and sometimes we think that it makes our food cook faster or it makes the water boil faster. But in reality, sodium chloride, if you recall from the solubility curves, is a pretty flat has a pretty flat slope. In other words, as the water temperature increases, not a lot more salt will dissolve into the water. And so even though we're adding salt to our water when we start the cooking process, let's say we want our pasta to cook a little faster, we can't get that much more salt to dissolve in the water as the temperature increases. And so the boiling point probably doesn't increase as much as we think it will. The fact remains that the salt is probably there more for flavor than it is to increase the boiling point. That being said, though, if you've got a really large pot of water, you add as much salt as you can to make it saturated. The boiling point would get high enough that instead of boiling at 100 degrees Celsius, it might boil at 105, 110 degrees Celsius. And if that's the case, then the food will cook faster because that temperature plateaus or stays constant for as long as the water is boiling. All right, so here we have a thermal image of two ice blocks. The one on the left has some salt sprinkled on the surface, and the one on the right does not. And we can see that, this is the tool that they're going to use to measure the temperature at the surface of these ice blocks. So let's see how the temperature of the ice is different. All right, so they're pointing it at the surface of the one with the salt, and it got down to about negative 16 degrees, whereas the one without the salt is only getting down to about negative 3.5 to 4 degrees Celsius. Okay. So the ambient temperature is around 18.5 degrees. All right. So thermal imaging shows that the temperature of the ice sample on the left that has the salt reaches a much lower temperature than the one on the right. And you might wonder why the ice block on the right doesn't get stuck or gets lower than 0. And it's because water is a very tough solvent to keep pure. So as it was freezing, it was probably absorbing a little bit of carbon dioxide from the air, and that additional solute in the water can cause the freezing point to be slightly below 0 degrees Celsius. The tab that I have open is at the top of assignment number 23, Colligative Properties. At this point, you should be able to answer the 10 questions that follow. If you need to look back at the presentation, you can do that. You can just click back through the slides to find the information that you need to answer the questions. All right, so I am going to go back to the course. Oops. And also remind you underneath the calendar that there is a practice test that's due on Wednesday as well. So I should be able to open the number 23 Colligative Properties assignment right now and see everybody logged into it and working on those questions while the information is fresh in your memories. And then the solutions practice can be a homework assignment, or I think most people would be able to get both of these done easily before the end of the hour if you don't want to have any homework. All right, so my expectation right now is that you're working on 23, the Colligative Properties.